This is basic integration rules. Now, recall we had the u-substitution and some of the different choices we'd try for the u-substitution. If you had a problem that had parentheses to a power, then you would try to let u equal to what's inside the parentheses. If you had a problem that had a radical of some sort, you try to let u equal to what's inside the radical. If you had a fraction of some sort, you try to let u equal to the denominator. If you had e to a power of some sort, where it's more than just a number, you let u equal to the power. Although there's a whole variety of different u substitutions you can do, these were kind of four big ones we worked with in Calc 1. Well, this section is about reviewing your techniques from Calc 1. So let's take a look at problems. Our first one, I got the integral of 5 over x minus 3 to the third power dx. Well, here we have parentheses to a power, so I'm going to let u equal to what's inside the parentheses, which is x minus 3. I'll take derivative of that. Derivative of x minus 3 gives me 1. And then I put dx on. Well, the dx is already there. The 1 is trivial. So the 5 I'll put out in front. And we're now ready to do our u substitution. So we replace the x minus 3 with u. So we've got 1 over u to the third. And then dx replaced with a du. Well, we can't leave that downstairs. So we'll take it up to the top, the numerator. And becomes u to the negative 3. Remember, when you move anything opposite of where it's at in a fraction, the sign of the exponent changes. Well, now we're going to add 1 to our power and divide by our new power. Plus c. Negative 3 plus 1 gives us negative 2. And negative 2 there. Now we, again, don't want any negative exponents, so I'm going to take the u to the negative 2 downstairs to the denominator. And we get 5 times 1 over negative 2 u squared plus c. Multiply that through, and I'll put the negative up on top, so that gives us negative 5 over 2u squared plus c, and u was x minus 3. So we got negative 5 over 2 times x minus 3 squared plus c. And that's our answer. Let's take a look at our next problem. We got the integral of x square root of 8x squared minus 3 dx. Okay. Whenever we have a radical, one u substitution we can try is let u equal to what's underneath the radical. So u is equal to 8x squared minus 3. Take derivative of that. That gives us 16x dx. Well, we have the x, we have the dx in there, but we don't have 16. So we'll put a 16 in there. Like that. And we have to offset it with a 1 over 16 out in front. Remember, you can always put a number inside, but you just got to offset it with the reciprocal of it out in front. And so now we're going to replace the 8x squared minus 3 with u. So this is the square root of u. The 16x dx we replace with du. I'm going to rewrite that as u to the 1/2 power du. And now we're ready to add 1 to our power, divide by our new power. So we'll add 1 to our power, and we'll divide by our new power. One half plus 1 gives us 3/2. We have 3/2 down here. If you got a single fraction downstairs, you flip it and multiply it times your top part. Excuse me. So we got 1/16 times 2 over 3 u to the 3/2 plus c. The 2 and a 16 cancel. It gives me 1 there, gives me 8 here. So that gives me 1 over 24. And u, we said, was 8x squared minus 3. So I got 8x squared minus 3 to the 3/2 power plus c. And that's our answer. Now let's take a look at this one. The integral of x minus 4 cube root of x squared minus 8x plus 1 dx. Well, we let u equal to what's under the radical. That's always a good thing to try. So u is equal to x squared minus 8x plus 1. Du, take the derivative of that, which would give us 2x minus 8 dx. And you always, if there's a number they have in common, you want to factor it out. Because you're trying to get it to match something in your problem. Now, I suppose it could have 2x minus 8 up here, and then you wouldn't want to factor it out. But well, now, I have the x minus 4 up here. I have the dx, but I don't have the 2. So I need to put a 2 inside and offset it with a 1/2 out in front. Okay. That's a 4 there. Now we're ready to do our substitution. The 2x minus 4 dx gets replaced by du, and this gets replaced by u, so we got 1 over the cube root of u du. Well, the cube root is u to the 1/3 power du. And we're going to take that u to the 1/3 up on top. And that becomes 1/2, and then u to the negative 1/3 du. Remember, you take anything opposite of where it's set in a fraction, sign of the exponent changes. And now it's u to a power. And what we're going for is these all revolve around. I don't have that formula on here. Huh. Well, never mind. But where you have u to a power. And if you have that, then like u to the n, then it becomes u to the n plus 1 over n plus 1. So again, we'll add 1 to our power and divide by our new power. Let's see. Negative 1/3 plus 1 gives us 2/3. So we got u to the 2/3 over 2/3 plus c. You got a single fraction downstairs. You flip it and multiply it times your top part, so it becomes 3/2 u to the 2/3 plus c, which gives us 3/4. And u, we said, was this x squared minus 8x plus 1. So we'll plug that back in. And that's 2/3 power plus c. And that's our answer. And I don't think I have room for another one there, so let me save that. problem was that? That was 3. Okay. Let's look at our fourth one. Got 5x over x plus 3 dx. Okay. Now, two different approaches you could take on this one. One of them is you could use long division and rewrite it. The other one is just set u equal to your denominator and see if that goes anywhere. Sometimes it does, sometimes it doesn't. So we'll set u is equal to x plus 3. du would equal 1 dx. Well, the 1's trivial, so I don't need to worry about it. dx is already there. The 5 we can put out in front. The x plus 3 gets replaced, but there's an extra x here. Well, what we do here is we solve this for x. So I'm going to take the 3 and move it to the left side. And we get u minus 3 is equal to x. So, our top problem here, again, I'll put the 5 out in front. The x up on top, we get replaced by u minus 3. The x plus 3 down below we said is u, and this is du. Well, before we had 2 terms down in the denominator, now we got 1 term, which is much better because we can split this up now. I can put u over u minus 3 over u du, which becomes 1 minus 3 over u du. Now the integral of 1 in terms of u is u minus an integral of 1 over u. The 3 just stays out in front. The integral of 1 over u is natural log of the absolute value of u. And then plus c. Well, now we need to plug our u back in. Over here we said u is equal to x plus 3. So we got x plus 3 minus 3 natural log of the absolute value of x plus 3 plus c. If I multiply that 5 through, 5 times x is 5x, 5 times 3 is 15, 5 times negative 3 gives us negative 15 natural log of the absolute value of x plus 3 plus c. Now, c is a constant. It's a number we don't know. And we have 15. We can combine those together. So we've got 5x minus 15, natural log of x plus 3. Now, c is a number we don't know. If we add 15 to a number we don't know, we still have a number that we don't know. So that's plus c. Anytime you just have single numbers sitting there, you can always merge those together to c just to become c. Because again, that's a number we don't know. And that's our answer. Let's take a look at our fifth example. We got cosine x over square root of sine x dx. Okay, now I come over to my my tables here. I started looking through my trig identities, and it doesn't look like there's anything that even looks close. You know, it's just like, how in the world did I work that? Well, go back to your basics. We said if you have radical, try to set u equal to what's in the radical. So we'll set u equal to sine x. Du, derivative of sine is cosine. And then we put on our dx at the end. Where's that? Derivative of sine is cosine. There it is. That's an equals right there. It looks like a negative, but it's actually an equals. I guess I can make that a little bit bigger. Maybe. There it is. That's better. So it looked like maybe it was a trig problem to begin with, and it does have trig in it, but all of a sudden it's going to be a different kind of u-substitution. We'll replace that with u. The cosine x dx gets replaced with du. So this will be 1 over square root of u du. And square root of u is u to the 1/2 du. And we're going to take the u to the 1/2 up on top. And that becomes u to the negative 1/2 du. And now we got u to a power. So we're ready to apply our formula. Formula says you add 1 to your power, divide by your new power. So I got negative 1/2 plus 1 divided by negative 1/2 plus 1 plus c. Well, negative 1/2 plus 1 is 1/2. So this becomes u to the 1/2 over 1/2 plus c. If you got a single fraction downstairs, you can flip it and multiply it times your top part. So I got 2 over 1 times u to the 1/2 plus c, which gives us 2u to the 1/2 plus c. And since this is a fairly simple radical, we'll put it back in that form. So this is square root of u. That's what u to the 1/2 means. And somewhere we said u was sine x. So this becomes 2 square root of sine x plus c. And that's our answer. Oops. Let's look at our next problem. This one kind of stumped me at first. I was trying to use an example they gave in the book. This example in the book was pretty cool, how they handled this, and didn't work quite right. And then I did a lot of thinking about it, and finally hit me. If I try to set u equal to the denominator, that'd give me du, which would have an e to the x in it. Well, let me go through the steps over here, and then I'll erase them. You know, we let u equal to the denominator 5e to the x minus 3. Du would equal to 5e to the x dx. Now the 8's trivial, so I don't need to worry about that, but I need an e to the x up on top. So I can multiply the top by the e to the x and the bottom by e to the x. And by doing that, I have to solve this for e to the x. So we get u minus 3 over 5 equals e to the x. And we would end up with something down below that we can't directly work with. So it just doesn't work very well. Doesn't mean you couldn't get there, but it just doesn't work. Well, a different technique is I'm going to try to rewrite this bottom part so that there's a plus 1 right here. And now first off, I could take that 8 and put it out in front if I wanted to, not worry about it. On the bottom part, I could, you could think of it as, well, let me show all the steps. I'm going to divide everything by a negative 3. I was going to skip steps. Okay. So we got 8. Oops. Except that's 1 now. We got 1 up on top, divided by negative 3. We got 5 divided by negative 3, e to the x. And then negative 3 divided by negative 3, dx. Well, the negative 1/3 I can go ahead and bring out in front. Not worry about that number on top, so that becomes 1 again. And this is negative 5/3 e to the x. And then this becomes plus 1. Now what I'm trying to achieve here is I'm trying to get this number up on top the same as the number down here. That's my goal. Now, first when I started tackling this, I left the 8 up here and I tried to get this as an 8 down here. And it hurt my head trying to do that. And then I started thinking about it more, and I thought it was a lot easier now. Just divide everything by -3, and you get a positive 1 here, and whatever you have up here you can put out in front, so it's all automatically 1. Okay, so that gives us -8/3. Now we got a 1 here and 1 here. I'm going to put a -5/3 e to the x up on top. So I got -5/3 e to the x up on top, and we already have a +1 up there. And -5/3 e to the x +1. Now notice my top matches my bottom now. Well, we can't just add that up on top. We have to offset it. So by putting a -5/3 e to the x here, we're going to put a +5/3 e to the x right beside it. Haven't changed any. These, if I went backwards, would cancel away. Well, now what we're going to do is we're going to merge or split this into a separate integral. So I have these I'll put over this denominator. So I got -5/3 e to the x +1 over -5/3 e to the x +1 plus, that's dx. And then I'll put this 5/3 e to the x here over the denominator. And then dx. Well, the reason I'm doing that is this becomes 1. So I got -8/3. This is the integral of 1 dx. And normally I might take this 5/3 and put it out in front, but I'm going to need it. And even more than that, I'm going to need a negative up there. And we'll see that once we set u equal to the denominator. The derivative of this, we're going to give us a negative. So I'm going to put a negative out in front, and then I'll put a negative up on top to offset that. There we go. So we got -8/3. I'll write it down again, then I'll do this. Like that. -5/3. E to the something. E to the x. And then down here we got -5/3 e to the x +1 dx. Okay, so this right here, I'm going to let u equal to the denominator, which would be -5/3 e to the x +1 du. The derivative of this, the 1 drops away, and derivative of e to the x just e to the x, and the number stays out in front. So that gives us -5/3 e to the x, and then we add on our dx, which works out perfect because we have the -5/3 e to the x up on top and dx here, so all that's going to be replaced by du, and the bottom part will be replaced by u. Well, the integral of 1 just gives us x minus, and I'm going to rewrite this first. This becomes 1 over u du. I'll add this plus c on here in a minute. So I've got x minus the integral of 1 over u is natural log of the absolute value of u plus c. And u, we said, was -5/3 e to the x +1. So we'll plug that back in. We'll get the absolute value of -5/3 e to the x +1 plus c. And we'll go ahead and multiply the -8/3 through. And we got -8/3 x plus 8/3 natural log of the absolute value of -5/3 e to the x +1. Then my plus c. Now sometimes I'll leave the number out in front, sometimes I'll multiply it through. I wish there was a consistency there, but sometimes there's not. Sometimes even with an absolute value, they'll factor out a negative, and then they'll change the signs around on that. We won't worry about that though. No, actually, if I did that, never mind. Let me save that. I was thinking we could maybe drop the absolute value bars, but I don't believe so, because e to the x could become very, very small, and then we would need them there. Oops. And what problem was that? That was problem 6. So let's look at 7. One plus sine x over cosine squared x. Now I have no memory. So when I was looking at these this morning, I already worked these in class, so I kind of have a general idea on some of them, but I couldn't remember this one. There's 2 ways you could go with it. One of them is you could rewrite the bottom part as 1 minus sine squared, and then factor it, and then 1 plus sine x would cancel with 1 plus sine x, and you'd have 1 over 1 minus sine x. But I don't think that really go anywhere, because we can't do a u-substitution then. So the other thing jumped out at me is we got a single item downstairs here. If you have a single item, there's no pluses or minuses separating anything, you can try to take each item up on top and put it over that single item. So we could rewrite this as 1 over cosine squared plus, green screen, let's try it again, 1 over cosine squared plus sine x over cosine squared dx. Well, you may be looking at this like, well, how does that help us? Well, 1 over cosine squared, that's secant squared. And if we come over here and look at our formulas, we should have a secant squared. Yeah, here it is, number 12. The integral of secant squared is tangent. So that one's already perfect. Now this one, 2 different ways we could do it. We got to do a u-substitution on the bottom. I think that's what I started doing in class, and somebody said, don't we have a formula for that? And I started looking closer at it. And let's see if that's true, though. So I'm going to rewrite this as sine x over cosine x times 1 over cosine x dx. Now I may end up erasing this. We'll see. Sometimes you just need to try and see if it goes anywhere. So here we have tangent x, secant x dx. Tangent x, secant x. Tangent x, secant x. Sure enough. See, I didn't see that in class. I was doing it the hard way. Somebody said, hey, you got a formula for that. So now these we can do directly. There's no u-substitution. Secant squared, remember, was tangent from here, property 12. So that's tangent x. And tangent x, secant x, the integral of it is secant from 14. And then you put your plus c on at the end. And that'd be your answer. So again, sometimes you may have to use some trig identities to simplify it. This one's the same one as that one. So why did I have this one? I suppose because it looked different. Let's talk about it, even though it is exactly the same as the last one. I try to make these problems up, and sometimes when I make them up, they don't come out perfect. Okay. Now, I got this right here. If I let u equal to the denominator, that's one of our techniques, the derivative of it would be give us a cosine, which we don't have up on top. Now, I could put a cosine up on top and then offset it with a cosine on the bottom, but that wouldn't go anywhere. Well, one of our trig identities, trig tricks, said if you got a trig expression of some sort downstairs and then plus or minus something else. One thing you could try, and it really is as vague as that, you could have sine x minus 1, sine x plus 1, even possibly maybe a sine x minus another trig. No, cosine x or tangent x or something. One thing to try, won't always work, but one thing to try is to multiply the top and bottom by the conjugate of the bottom. Conjugate, first is the same, second is the same, sign in the middle changes. So we'll multiply top and bottom by sine x plus 1. And when we do that, we got a sine x plus 1 up on top, and down below, neat part about conjugates is all you have to do is multiply your first parts and last parts. Sine x times sine x is sine squared, and negative 1 times 1 gives us negative 1 dx. Well, the reason why we multiply by the conjugate is so we can then use one of our properties. Remember, we had sine squared plus cosine squared is equal to 1. If I take the sine squared to the right side, we get cosine squared is equal to 1 minus sine squared. Actually, I did that wrong direction. Let me try it again. Probably should have a script right here so I never screw up. But it helps actually look what you're trying to achieve. We want sine squared minus 1. So I'm going to take the 1 over to here, and I'll take the cosine squared over to here. I guess this is slightly different than the other one. So when I take the 1 over, then it becomes a negative 1. Take cosine squared over, and it becomes a negative. So this sine squared minus 1 right here, we could replace with negative cosine squared x. So what made me think these were the same to begin with? Oh, 1 plus sine x minus 1. Okay. Well, what's the benefit of this? We went through all this and still got a mess. Well, we got a single item downstairs here. So what we can do is we can split this up. We can put sine x over negative cosine squared, and that's dx. And we can put 1 over negative cosine squared dx. The negative I can go ahead and put out in front, so I don't need to worry about it. And then this we can rewrite as sine x over cosine x times 1 over cosine x. This one, take negative, put it out in front, and we can rewrite this as secant squared. I'm not really referring to these properties, I guess, but sine over cosine is going to be tangent. 1 over cosine is secant, and that's where I'm getting those. So this becomes tangent x secant x, like that. Well, we just looked at these formulas, so I won't flip back to them. The integral of tangent secant x dx, I'm bad about dropping those, is secant, minus, and then the integral of secant squared is tangent x, and then plus c. So again, very, very close to that last one we just did. And let's take a look at this one. Integral of 1 over x minus 1 square root of 9x squared minus 18x plus 4 dx. Okay. We got a radical, so we set u equal to the what's under the radical. We do that, du would be 18x minus 18. I could factor out an 18, and this one actually I think works. No, let me see. I don't think it does. minus 18x plus 4 du would equal to 18x minus 18. I can factor that out. Okay, it gives us an x minus 1, but doesn't give us an x minus 1 downstairs. So it doesn't work. Didn't think it did. Pretty much, if you set u equal to a radical, and it has anything beyond just giving you a simple number when you take the derivative, you have to have x's up on top. So let's go over to our formulas. I'm looking through my formulas. I'm looking for a square root downstairs, and maybe some kind of x in front. So square root downstairs, that's 16 and 18 here. Now 16 doesn't have a variable out in front. Now 18 implies that u there is going to have a variable out in front. So we're going to try to get it to match this formula. So we're going to have u squared minus a squared, and then a u out in front. Well, we're going to use complete and square for this. And I'm going to factor out a 9 on that first. I'm not very good when you got numbers involved there. So factor out a 9, and that gives us, a number before your x squared. Factor out a 9, that gives us x squared minus 2x plus 4/9 dx. Gives us 1 over x minus 1. And 9 we can bring out in front as a 3. And we're left with x squared minus 2x plus 4/9 dx. Okay, so let's complete the square on what's inside the radical. So we take the number before the x, which is negative 2, multiply it times a half and square it. Well, negative 2 times a half is negative 1, and negative 1 squared is 1. Now this 3, I'm just going to go ahead and put it clear out in front. I'm pretty sure I won't ever need it inside. If so, we can bring it back in. So this right here becomes x squared minus 2x, and we add a 1, so that's what we just found right here. I'm going to group those together. And to offset that adding 1 there, we have to do a minus 1. Then the plus 4/9 carries along. And we're going to actually group those two together. So whatever number you find here that you're adding, you group that with the x squared minus 2x. Now if I were to go backwards, I haven't changed anything. Negative, or 1 minus 1 is 0. So it's still the same value as this. Okay. So then this becomes x minus 1. And this actually factors x minus 1 squared. And combining these together, this is a mixed number. I take negative 1 times 9, gives us negative 9. And plus the 4 gives us negative 5. So this would be negative 5/9 dx. Now how I got the x minus 1 is whatever number is right here, right before you square it, is always what goes right here. So very easy to factor. It's also not very hard to factor just normally. But that little trick makes it even easier. Okay, I think we're close. U squared minus a squared. This would be u squared minus, we need to rewrite this as something squared. And you can always rewrite it as something squared by putting a square root around it. Because if I were to go backwards, the second power and the square root cancel each other out and leave you the 5/9. And so now we have it, and I'm not gonna simplify that. U would equal to x minus 1. Replace that with u. Trying to get it to match this formula. A is going to equal the square root of 5/9. Du, derivative of x minus 1 is 1 dx. So 1's trivial. We've got the dx there. So let's start plugging things in. This x minus 1 here becomes u. Then we've got square root, that becomes u. So we've got u squared minus, this is a, so that's a squared. And dx gets replaced by du. Now it matches our formula exactly now. So from our formula, that says, which one is it? This one. We rewrite it as 1 over a arcsecant the absolute value of u over a plus c. Okay. So then we'll plug in our values. A, we said, was square root of 5 over 9. Then we got arcsecant. Absolute value of u is x minus 1, over square root of 5 over 9, plus c. And I want to do a little bit of simplifying. That square root of 5/9, I can split up into the square root of 5 over square root of 9. Arcsecant, absolute value of x minus 1 over square root of 5 over square root of 9 plus c, which gives us 1/3 times 1 over square root of 5 over 3. Arcsecant, absolute value of x minus 1 over square root of 5 over 3 plus c. Now here I've got a single fraction downstairs, so we'll flip it and multiply it times your top part. So that becomes 3 over square root of 5. Arcsecant, do the same thing here. So this becomes 3 over square root of 5, absolute value of x minus 1 plus c. Well, in this first part here, those cancel. We don't want the square root of 5 downstairs, so we multiply top and bottom by the square root of 5. And that gives us square root of 5 over 5. Arcsecant. And here, we don't want the square root of 5 downstairs, so we multiply top and bottom by it. And we get 3 square root of 5 over 5. Absolute value of x minus 1 plus c. And that would be our answer. Yeah, let me save that. Why does it do that? Well, I know why. The program's not written very well. Let's take a look at the next one. One over x squared minus 6x plus 50 dx. Okay, if we did our basic, let me grab a drink first. Now, if we did our basic u-substitution, we set u equal to the denominator. We wouldn't go anywhere. The derivative of that would give us 2x minus 6, and there's no way I can get that out of the top. I can't split this in separate fractions because these minuses and pluses down here, everything would have to be multiplication. So that doesn't seem like I can go anywhere. Come back to our rules. There we go. We don't have very many from Calc 1. E to the u, sine u, cosine, no. There's no radical downstairs, no. 17's maybe. 18, no radical downstairs. Has to be 17 is what we're going to try to get it to look like. So we want to rewrite as a squared plus u squared. Well, we have to use a completeness square again. So what we're going to do is we're going to take the number of this before x, which is negative 6, and multiply it times a half and square it. Negative 6 times a half is negative 3, and negative 3 squared gives you 9. So we're going to add the 9. So we got x squared minus 6x plus 9 And these we want to group together. Now if I add 9 here, I'm going to offset it with a minus 9 right beside it. And then plus 50s at the end. And these will be grouped together. Well, this first part factors as x minus 3 squared. Again, the trick on it is whatever number's right here, sign included, is always what goes right there. Not that it was that hard to factor it anyway, but negative 9 plus 50 is 41 dx. Excuse me. Put 41 first. We get x minus 3 squared. We're wanting to achieve this, u squared, and then we want an a squared here. So we're going to try to write that as something squared. So I come over here. And again, we can always put a square root around it, like that. And now I think we're ready. Remember, a square root and a second power cancel each other away, so we haven't changed any. Still equal to 41. So our a is going to equal to square root of 41. Our u is going to be what's inside of parentheses here, which is x minus 3. And du, derivative of that is 1 with a dx. So we've got dx. So then this becomes 1 over a squared plus u squared du, which matches our formula perfectly. They put du up on top, but on top of the side, same difference. So formula says we're going to rewrite that as 1 over a arctangent the u over a plus c. There we go. Well, a we said was square root of 41, so I have 1 over square root of 41 arctangent. U we said was x minus 3, and a is square root of 41, then plus c. Well, I don't want to leave the square root of 41 downstairs, so multiply top and bottom by that, so that gives us square root of 41 over 41 minus arctangent, and here I multiply top and bottom by square root of 41 over 1, and we get square root of 41 over 41. I'll learn to speak someday. And x minus 3 here, plus c. And that's our answer. Let's look at our next problem. Okay, so we got 2 over square root of 3 minus 8x minus x squared dx. Okay, our standard u substitutions. You've got a radical, let u equal to the radical, or what's underneath the radical. So u is equal to 3 minus 8x minus x squared. Doesn't go anywhere. If I find du, then I can't do anything with it. We could also set u equal to the denominator. That's even worse. That isn't going anywhere. So then we go to our formulas. Looking for a square root downstairs. No. Here's a radical downstairs. Possibility number 16. This one, no radical downstairs, no. So, or it could be 18. Now 18 has a u out in front of it. That would imply that we have a variable out here. We don't have a variable out here. So we want to use number 16. So we want to rewrite that as a squared minus u squared. Now, I have some problems with factor or completing a square when I have a negative before my x squared. So I'm going to first rewrite it in the standard form. Largest power down to smallest. And then I'm going to factor out a negative 1. Now, I don't have to factor it out of the plus 3, but I definitely need to factor out of the first two. So this becomes x squared plus 8x. And plus 3 just remains. Okay. So let's complete the square now. Take the number of this before x, which is 8, multiply it times a half and square it. That gives us 4 squared, or 16. So we're going to have negative 1 times x squared plus 8x plus 16 and again we're going to consider that one group together, and I can't just add a 16 in there willy-nilly, so I have to put in a negative 16 right beside it. Close parentheses, plus 3. Okay. Now what I'm going to do is I'm going to take this negative 1 here, it's out in front of the parentheses, I'll multiply it times my first group, and I'll multiply it times my second group. So I'm going to have negative 1 times x squared plus 8x plus 16, and we'll have negative 1 times negative 16 plus 3 dx. So this becomes negative 1. Now I'm going to go ahead and factor this. This factors as x plus 4 squared. Negative 1 times negative 16 is positive 16 plus 3 dx. Which gives us square root of negative 1, x plus 4 squared, and 16 plus 3 is 19 dx. Remember with the if you got a negative 1 in front of parentheses like that, it's multiplication, you don't need to put the 1. So we got negative x plus 4 squared plus 19 dx. Okay, real close now. We want this as a squared minus u squared, so we want the number first. Well, that's okay, we can flip those around. So that becomes 19 minus x plus 4 squared dx. Well, yeah, I can probably do it here. I probably have enough room. The 2 I'm going to go ahead and bring out in front. I don't need a 2 in there. The formula doesn't have 2 in there anywhere. But I do need this as a squared. So I'm going to rewrite the 19 as the square root of 19 squared minus x plus 4 squared dx. Remember 19, to write that as something squared, you can always put a square root over it and then raise it to the second power. Because when going backwards, those will cancel each other away and just leave you the 19. Well, now everything's in a perfect form. So a is going to be square root of 19. U is going to be equal to x plus 4. And derivative of x plus 4 is 1 dx. So this becomes 1 over the square root of a squared minus u squared du, which matches our formula perfect. So we're going to rewrite it using this. 2 stays out in front, and this becomes arc sine u over a plus c. Okay, so we got 2 arc sine u was x plus 4 over a, which was square root of 19, and then plus c. The last thing, we don't want that square root of 19 downstairs, so we multiply top and bottom by the square root of 19, and we get square root of 19 over 19 times x plus 4 inside the arc sine. And that's our answer. And it looks like I need to start a new page. Yep. Time for my tablet to blow up. Okay, so let's look at our next problem. Let's see, 1 to e 5 plus natural log of x over 3x dx. Okay. Let u equal to the denominator. Doesn't go anywhere. Grab a drink. I try to let u equal to maybe, well, no matter what, my standard substitutions don't seem to work. Now, sometimes, if you're drawing a blank on your standard substitutions, come up and look at your derivatives. That'll help trigger, well, what should you do? If we look at the derivative of natural log of x, we're going to see something that'll help us in this. And I have no clue where that's at. Here it is. Well, that formula is not great, but natural log of x would give us 1 over x. 1 over x. Well, that's what this x is down here. So this kind of defies what we normally are used to doing for u substitution. We let u equal to the numerator, the top part. So then, the derivative, the 5 drops away. Derivative of natural log of x is 1 over x dx. Well, we can't have the 3 downstairs, so I'll take that and put it out in front. Remember, numbers you can freely take in and out of your integration. And we got 5 plus natural log of x over x dx. And again, that's like 5 plus natural log of x times 1 over x dx. You can split up that fraction in that manner. And here's my 1 over x dx. That's going to be replaced by du, and this will be replaced by u. Now I'm going to put x equals 1 here and x equals e, so we don't lose track of those x values. And this here becomes u, and this here becomes du. Well, we'll add 1 to our power, divide by our new power. So that becomes 1/2 u squared. X is equal to e, and x is equal to 1. Now u up above we said was 5 plus ln of x. So we'll plug that back in now. The 1/2, let me go ahead and put that out in front so I don't have to worry about it. So we got 5 plus natural log of x squared. And these are now back to x values. So 1 to e. Well, that gives us 1/6. And here I could plug in these values. So that gives me 5 plus ln of e squared minus 5 plus ln of 1 squared. Well, natural log of e gives you 1. And natural log of 1 gives you 0. So we'd have 5 squared. So it gives us 1/6. 5 plus 1 is 6. We got 6 squared minus 5 squared, which gives us 36 minus 25. Which gives us, what is that, 11? So our answer, assuming I didn't make a basic math error somewhere, is 11/6. And it's always questionable whether I add and subtract and multiply correctly. There we go. And believe that is the last slide. Yes, we're at the end of that section. So let me stop the recorders.